In the soft green hills of southwestern Scotland, where morning mist rises from lochs like breath from sleeping earth, where stone walls mark boundaries that have stood for centuries, where silence settles into valleys as naturally as water, a child was born who would one day hear what others could not hear. The hidden music connecting all things luminous and all things magnetic, the invisible symphony playing through every corner of space. James Clerk Maxwell entered the world on June 13th, 1831, in Edinburgh. That city of grey stone and philosophical tradition, where the Scottish Enlightenment had flourished, and where ideas were taken as seriously as commerce. But Edinburgh was merely birthplace. The landscape that would shape young Maxwell's soul was Glenlair, his family's estate in Galloway, where his father had built a house, and where the natural world became the boy's first teacher, his first temple, his first source of questions that would never cease demanding answers. The Glenlair estate spread across gentle countryside, fields and forests, streams and hills, the kind of landscape that invites walking and wondering. John Clerk Maxwell, James's father, was a man of practical interests, a lawyer who preferred country life to Edinburgh's bustle, who occupied himself with agricultural improvements and mechanical devices. He passed to his son not formal scientific training, but something perhaps more valuable. The habit of noticing, the practice of asking why things work as they do, the conviction that the world rewards careful observation with understanding. Young James was peculiar from the beginning, not peculiar in ways that troubled. He was cheerful, affectionate, beloved by those who knew him, but peculiar in his relentless curiosity, in the questions that emerged from his mind like water from an inexhaustible spring. "What's the go of that?" was his constant inquiry, the Scottish child's way of asking how things worked, why things happened, what invisible mechanisms drove the visible world. When adults could not answer, and they often could not, he would follow with, "But what's the particular go of it?" Pressing deeper, unsatisfied with surfaces, hungry for essences. The world of Glenlair offered endless material for questioning. Why did the sun set in different places at different seasons? Why did water run downhill but mist rise upward? Why did mirrors reverse left and right but not up and down? Why did magnets attract iron but not copper? Why did rubbing amber on cloth make it attract bits of paper? The questions tumbled forth without pause, without embarrassment, without the self-consciousness that silences curiosity in so many children as they learn that asking too much marks one as strange. His mother, Frances K. Maxwell, encouraged the questioning. She was educated, curious, a watercolorist who saw the world with artist's attention to light and form. She undertook James's early education herself, teaching him to read, introducing him to natural history, nurturing the wonder that seemed native to his character. The mother-son bond was deep, their shared curiosity a bridge between generations. But Frances died when James was 8 years old. The cancer that took her came quickly, leaving the boy and his father alone in the house at Glenlair, alone with their grief, alone with the silence where her voice had been. The loss marked Maxwell permanently, not with bitterness or despair, but with a kind of seriousness beneath his natural cheerfulness, a recognition that life was fragile, that time was limited, that what mattered must be pursued with full attention because nothing was guaranteed. After his mother's death, James's education became more formal but less successful. His father, uncertain how to proceed, engaged a tutor whose methods were harsh and whose understanding was limited. The tutor could not comprehend a child who asked questions beyond the curriculum, who wanted to know not just what, but why, who seemed to see connections invisible to ordinary eyes. The arrangement ended badly, the tutor dismissed. Young James sent to Edinburgh Academy, where his peculiarities would find different reception. Edinburgh Academy was a prestigious institution, training ground for Scotland's elite, rigorous in classical education, but suspicious of unconventional minds. Maxwell arrived wearing clothes his father had designed, practical, comfortable, utterly unlike the fashions of Edinburgh boys. His rural accent, his homemade attire, his strange questions marked him immediately as outsider. The other boys called him dafty, Scottish slang for simpleton, unable to see that what they mistook for foolishness was actually perception beyond their capacity. But Maxwell endured, and more than endured. Within the academy he found friends who could appreciate his peculiar gifts. Peter Guthrie Tate, who would become significant physicist in his own right, and Lewis Campbell, who would become Maxwell's biographer. These friendships, forged in adolescence, would last lifetimes, would survive distance and divergent careers, would remain anchors throughout Maxwell's too short life. At 14, Maxwell presented his first mathematical paper to the Royal Society of Edinburgh. The paper concerned the geometry of oval curves, specifically a method for drawing perfect ovals using pins and string, generalizing the well-known method for drawing ellipses. The mathematics was elegant, the insight genuine, the presentation so impressive that many refused to believe a 14-year-old had produced it. The paper was presented by an adult on Maxwell's behalf, since the society could not quite accept a schoolboy lecturing to its distinguished members. The paper on ovals was not revolutionary, did not change mathematics or physics, but it revealed something essential about Maxwell's mind, the ability to see geometric relationships, to translate visual intuition into precise mathematical form, to find unexpected connections between seemingly simple phenomena and deeper structures. The abilities that would later unify electromagnetism were already present in the boy contemplating curves. As adolescence progressed into young adulthood, Maxwell's path became clearer. He would pursue natural philosophy, what we now call physics, and he would pursue it through mathematics, through the precise language that could capture what words could only gesture toward. The decision was not rebellion against his father's wishes. John Clerk Maxwell supported his son's intellectual pursuits, was proud of the accomplishments, encouraged the continued development. Father and son remained close, their bond strengthened perhaps by shared loss, by the absence that had shaped them both. We close this chapter as Maxwell prepares to leave Scotland for Cambridge, for the ancient university where Newton had walked, where mathematical physics had achieved some of its greatest triumphs, where the next phase of Maxwell's formation would unfold. The boy who asked, "What's the go of that?" was becoming a young man equipped with tools to find answers. The questions had not diminished, had only become more precise, more demanding, more capable of being answered through the methods he was learning to master. The Scottish mists would remain in Maxwell's heart throughout his life. Glenlair would call him back, would be the place where he would return to think most deeply, where he would eventually return to die. But first, the wider world awaited, the world of universities and scientific societies, of experiments and equations, of mysteries that had puzzled humanity for centuries and would yield their secrets to the boy from Galloway who had learned to listen to light. The hills of Glenlair, the questions without end, the mother's death that cast shadow and seriousness over natural cheerfulness, the father's support that made pursuit of knowledge possible, the peculiarity that was actually perception, the boy becoming the man who would change how humanity understands the universe. The foundation was laid, the curiosity was trained, the mathematical language was being learned. What remained was the great work itself, the unification that awaited in Cambridge's ancient halls and in the quiet study at Glenlair, where Maxwell would spend his most productive years. The boy who listened to light, who heard what others could not hear, who would translate that hearing into equations that still describe reality today. The beginning of the story, forever marked by Scottish mists and childhood wonder, forever the foundation upon which everything else would be built. The spires of Cambridge rise above the fenlands like prayers made permanent in stone, their Gothic architecture reaching toward heaven, as if mathematics and theology were merely different names for the same aspiration. Within these ancient walls, where Newton's ghost inhabits every quadrangle, and where the pursuit of truth has been sacred calling for centuries, young James Clerk Maxwell arrived in 1850 to discover the language that would unlock the universe's deepest secrets. Cambridge in the mid-19th century was a peculiar institution, beautiful and rigid, brilliant and provincial. The university maintained traditions stretching back to the 13th century, traditions of classical education, of Anglican religious observance, of mathematical training that had produced some of history's greatest natural philosophers. Trinity College, where Maxwell enrolled, was Newton's college, and Newton's presence saturated the atmosphere. To walk through Trinity's great court was to walk where Newton had walked, to study in library where Newton had studied, to feel the weight of expectation that genius creates for those who follow. The mathematical training at Cambridge was intense, was specialized, was unlike education anywhere else in the world. The mathematical tripos, the examination that sorted students into ranked order, demanded not merely understanding, but virtuosity, not merely competence, but creative problem-solving under extreme time pressure. Students spent years preparing for examinations that would determine their futures, that would rank them publicly from senior wrangler at the top to wooden spoon at the bottom, that would shape their careers and reputations permanently. Maxwell entered this pressure cooker environment with gifts that were obvious but unconventional. His mathematical ability was profound, but his approach was not the mechanical drilling that produced high tripos rankings. He thought geometrically, visually, seeking to understand the physical meaning behind mathematical formalism rather than simply mastering techniques for solving standardized problems. This approach would later prove revolutionary, but in the context of Cambridge examinations, it was sometimes liability. Yet Maxwell thrived, made friends among the most brilliant students of his generation, joined the Apostles, that secret intellectual society whose members included some of the finest minds of Victorian England, engaged in the debates about religion, philosophy, science, politics that animated undergraduate life, maintained his cheerful disposition, his willingness to ask seemingly naive questions that turned out to be profound, his combination of social warmth and intellectual depth that made him beloved companion. His tutor at Cambridge was William Hopkins, the most successful mathematical coach of the era, who recognized Maxwell's unusual abilities and adapted his teaching accordingly. Hopkins later said that Maxwell was unquestionably the most extraordinary man he had met at Cambridge, high praise from someone who had trained many of the period's leading mathematicians. The recognition helped Maxwell navigate the system without being crushed by it, allowed him to develop his distinctive approach while still acquiring the technical skills the tripos demanded. The mathematical tripos of 1854 ranked Maxwell second wrangler in Cambridge terminology. The senior wrangler that year was Edward Ruth, a superb technical mathematician who would become renowned coach in his own right. The ranking disappointed some who had expected Maxwell to take first place, but the examinations did not measure what Maxwell was best at. His strength lay not in rapid problem-solving under time pressure, but in deep contemplation of fundamental principles, in seeing connections that others missed, in the creative synthesis that would produce his greatest work. More revealing than tripos ranking was the Smith's Prize examination, which occurred shortly after. The Smith's Prize tested mathematical physics specifically, demanded original thinking rather than just trained technique. Maxwell tied for first place, and the examiners noted that his solutions showed physical insight beyond mere mathematical facility. The prize confirmed what those who knew Maxwell already understood, that his gifts were for understanding nature, not just for manipulating symbols. But what was the nature he sought to understand? Cambridge's mathematical physics curriculum covered mechanics, optics, astronomy, heat, the established domains of physical theory. Maxwell excelled in all of them, but his deepest interests were drawing him toward territories less thoroughly mapped. Electricity and magnetism were still fragmented fields, collections of empirical laws without unified theoretical framework. The connection between electric and magnetic phenomena, demonstrated by Ørsted and Faraday through experiments, lacked mathematical expression. Here was mystery worthy of Maxwell's gifts. During his Cambridge years, Maxwell began reading the papers of Michael Faraday, that self-taught genius whose experimental discoveries had transformed understanding of electricity and magnetism, but whose ideas remained controversial because he could not express them mathematically. Faraday spoke of lines of force, invisible curves filling space around magnets and electric charges, guiding interactions through what appeared to be empty void. The images were vivid, were physically intuitive, but were dismissed by many mathematical physicists as mere metaphor, as poetry rather than science. Maxwell saw something different in Faraday's work, saw not woolly thinking, but profound physical insight expressed in the only language Faraday had available, saw the possibility that Faraday's field concepts might be exactly right, might capture something essential about how electromagnetic forces actually work, might merely require translation into mathematical form to be recognized as revolutionary. The possibility lodged in Maxwell's mind would grow over years, would eventually produce the unified theory that changed physics forever. But that achievement lay in the future. For now, Maxwell was completing his education, absorbing the mathematical methods he would need, developing the physical intuition that would guide his theoretical work. He graduated from Cambridge in 1854 and was elected Fellow of Trinity College, securing the academic position that would allow continued research. The fellowship provided modest income, required no specific duties, offered the precious gift of time, time to think, to read, to calculate, to contemplate the mysteries that had seized his imagination. The years immediately following graduation saw Maxwell working on several problems simultaneously. His paper on Faraday's lines of force appeared in 1856, introducing the mathematical machinery that would eventually describe electromagnetic fields. His work on color vision progressed, revealing the three receptor basis of human color perception. his analysis of Saturn's rings demonstrated that they must be composed of many small particles rather than solid or liquid sheets, a prediction later confirmed by spacecraft observations. The breadth was remarkable, the depth equally so. Maxwell was becoming the physicist who could see unity beneath diversity, connection beneath apparent separation. Cambridge had given Maxwell more than mathematical training, had given him community of brilliant minds, had given him confidence in his own unconventional approaches, had given him the institutional position that would support his research for years to come. The Cathedral of Numbers had initiated him into its mysteries, had equipped him with the tools he would need for his greatest work. We close this chapter as Maxwell leaves Cambridge for his first professorial position at Marischal College in Aberdeen. He was 25 years old, already recognized as exceptional talent, already pursuing the questions that would lead to electromagnetic unification. The training was complete. The preparation was finished. What remained was the great work itself, the spires of Cambridge, the pressure of examinations, the ghost of Newton hovering over Trinity College, the discovery of Faraday's papers and the recognition of their significance, the fellowship that provided time for thought, the foundation for everything that would follow. The Cathedral of Numbers had done its work, had transformed the curious Scottish boy into equipped scientist, ready to reveal the universe's hidden harmonies. The mathematics was learned. The physical intuition was developed. The great questions were identified. Now came the seeking. Now came the years of concentrated effort. Now came the unification that would change how humanity understands light and force and the invisible structures that fill all space. Before Maxwell could translate the invisible into equations, another seeker had to perceive what was there to be translated. This chapter belongs to Michael Faraday, the bookbinder's apprentice who became one of history's greatest experimental scientists, who saw patterns in empty space that others insisted were not there, who prepared the way for Maxwell through decades of patient observation and inspired intuition. Michael Faraday was born in 1791 in Newington Butts, a village south of London, to a blacksmith father whose poverty meant that young Michael received only the most basic education. At 14, he was apprenticed to a bookbinder, a trade that would seem far removed from scientific discovery. But the bookshop gave Faraday access to books themselves, to the ideas bound between the covers he was learning to stitch. He read voraciously, was particularly drawn to works on science, began conducting simple experiments based on what he read. The turning point came in 1812 when a bookshop customer gave Faraday tickets to lectures by Humphrey Davy, the famous chemist, at the Royal Institution. Faraday attended, took detailed notes, bound those notes into a book, and sent the book to Davy with a request for any position in Davy's laboratory. The audacity was remarkable. A working-class apprentice approaching one of Britain's most celebrated scientists. But Davy recognized something in the notes, something in the eagerness. When a position opened in 1813, Davy hired Faraday as laboratory assistant. The Royal Institution became Faraday's universe. The laboratory where Davy conducted experiments became Faraday's classroom, his workshop, his cathedral. He learned chemistry through direct involvement in Davy's research, learned experimental technique through practice, learned to see what careful observation could reveal. By the 1820s, Faraday was conducting independent research, was making discoveries that would establish his own reputation, was becoming a scientist rather than merely an assistant. In 1821, Faraday made his first great electromagnetic discovery. Hans Christian Ørsted had recently shown that electric current deflects compass needle, that electricity and magnetism were somehow connected. Faraday investigated this connection, discovered that a current-carrying wire would rotate continuously around a magnet, and that a magnet would rotate around a current-carrying wire. He had created the first electric motor, however primitive, had shown that electromagnetic forces could produce continuous motion, could do mechanical work. But Faraday was not satisfied with practical invention. He wanted to understand what was happening, how electric current created magnetic effects, what invisible connection linked the two phenomena. The question would occupy him for decades, would lead him to discoveries that transformed physics, would generate concepts that he lacked the mathematical language to express precisely, but that he perceived with uncanny clarity. The breakthrough came in 1831 with the discovery of electromagnetic induction. Faraday found that moving a magnet through a coil of wire induced electric current in the wire. That magnetism could create electricity, just as Ørsted had shown that electricity could create magnetism. The reciprocity was beautiful, was fundamental, was the basis for all electrical generators and transformers that would later power industrial civilization. The discovery established Faraday as one of the era's great scientists, earned him recognition, honors, offers of lucrative positions he refused because they would take him from his beloved laboratory. But what most distinguished Faraday was not his discoveries themselves, but how he understood them. Where other physicists saw forces acting at a distance, electric charges pulling on each other across empty space, magnets attracting iron through invisible, instantaneous connection, Faraday saw something different. He saw the space between objects as filled with something, with invisible structure that carried the forces, that mediated the interactions. He called this structure lines of force. The lines of force were visualized through simple experiment. Sprinkle iron filings on paper above a magnet, tap the paper, and the filings arrange themselves into curved patterns that trace out what Faraday called the magnetic lines of force. The patterns were not merely visual convenience. Faraday believed they represented something physically real, believed the space around the magnet was genuinely different from space far from any magnet, believed forces propagated through these lines rather than acting instantaneously across empty distance. The concept was revolutionary, was also deeply controversial. The mathematical physicists of the era, continental scientists trained in the French tradition of precise mathematical analysis, dismissed Faraday's lines of force as confused thinking, as failure to understand the mathematical formalism that properly described electromagnetic phenomena. Faraday had no mathematics, they pointed out. His lines of force were pictures, were metaphors, were not proper science. The action at a distance framework that described gravitational attraction worked perfectly well for electromagnetic forces. Why introduce confusing new concepts? Faraday defended his vision, but could not prove it mathematically. Could only argue from physical intuition, from experimental evidence, from the conviction that empty space was not truly empty, that fields were real physical entities, that forces required time to propagate through space rather than acting instantaneously. The arguments were not convincing to those who demanded mathematical proof. Faraday's reputation as experimentalist was unassailable, but his theoretical ideas remained marginal, tolerated rather than accepted. The frustration must have been profound. To see so clearly what others could not see, to perceive the invisible structure filling all space, to know that the mathematics would eventually confirm what intuition already grasped, but to lack the language, to be unable to express the vision in forms that skeptics would accept, to watch ideas dismissed as poetry when they were actually profound physics. As Faraday aged, his health declined. The mental energy required for sustained research faded. Memory began to fail. The meticulous experimentalist who had kept careful notes throughout his career found himself forgetting what he had written, repeating experiments he had already performed. He withdrew gradually from active research, continued lecturing when health permitted, maintained his position at the Royal Institution until almost the end. He died in 1867, having changed physics through his discoveries, but uncertain whether his deepest ideas would survive him. But across the British Isles, a younger scientist had been reading Faraday's papers, had been pondering the lines of force, had recognized in Faraday's physical intuition something not confused, but profound. James Clerk Maxwell saw that Faraday's field concepts might be exactly right, might merely need translation into mathematical language to reveal their full power. The translation would take years, would require mathematical innovations, would demand physical insight equal to Faraday's own. But Maxwell was preparing, was developing the tools, was readying himself to give Faraday's visions the mathematical expression they deserved. We close this chapter with Faraday in his final years, uncertain of his legacy, hoping someone would understand what he had seen. The lines of force waited in the space around every magnet, every current-carrying wire, every charged object. The fields filled the void, real though invisible, structured though intangible. The revolution Faraday had begun awaited its completion. The bookbinder's apprentice, who became great scientist, the experiments that revealed electromagnetic connection, the lines of force traced in iron filings, the vision dismissed as poetry, the hope that someone would understand. Faraday had done what experimentalists could do, had discovered, had observed, had perceived. Now the theorist must take up the work, must translate vision into equation, must prove mathematically what Faraday had grasped intuitively, the lines of force, the fields that filled space, the invisible structure of reality, waiting for their translator, waiting for Maxwell. In the quiet of his study, surrounded by papers covered in mathematical symbols that looked like ancient runes encoding cosmic secrets, James Clerk Maxwell began the work that would unify electricity, magnetism, and light into single theory. The years between 1855 and 1865 saw Maxwell gradually construct the mathematical framework that would reveal electromagnetism's hidden unity, that would show the universe more connected than anyone had imagined. The work began with Faraday's lines of force, with the attempt to express mathematically what the experimentalist had perceived physically. Maxwell's first paper on the subject, on Faraday's lines of force, appeared in 1856, when Maxwell was 25 years old. The paper introduced mathematical machinery for describing fields, for treating the space around electric charges and magnets as having structure, as containing something that mediated forces. The mathematics was provisional, was analogical, drew comparisons between electromagnetic fields and the flow of incompressible fluids through tubes. But the approach was revolutionary, took Faraday's images seriously as physics rather than dismissing them as mere visualization. The paper attracted attention, but did not yet reveal the full unification. That would require deeper analysis, more sophisticated mathematics, sustained concentration over years. Maxwell continued the work while teaching at Marischal College in Aberdeen, then at King's College London, then back at Cambridge. The institutional moves created disruption, but did not halt the fundamental research. The questions were too compelling, the progress too tantalizing, the sense of approaching something profound too powerful to abandon. The key breakthrough came through careful analysis of what the existing laws of electricity and magnetism actually implied. Coulomb's law described how electric charges attracted and repelled each other. Ampere's law described how electric currents created magnetic fields. Faraday's law described how changing magnetic fields induced electric currents. Each law had been established through experiment, had proven reliable in its domain. But were they consistent? Did they form coherent theoretical structure? Maxwell discovered that they did not. Not quite. The existing laws contained mathematical inconsistency, a flaw that revealed something missing from the picture. The inconsistency involved situations where electric fields changed over time. In such cases, the equations predicted results that violated fundamental conservation principles that gave different answers depending on how calculations were performed. The mathematics itself was saying that something was wrong, that the existing laws were incomplete. The resolution required adding something to the equations, a term representing the effects of changing electric fields, a contribution that created magnetic effects even in absence of actual current flow. Maxwell called this addition the displacement current, because it behaved mathematically like current flowing through space itself, like the displacement of something in the electromagnetic field. The addition was necessary for mathematical consistency, but it also had physical consequences no one had anticipated. With the displacement current included, Maxwell's equations became complete and self-consistent. The mathematics was elegant, was unified, described all electromagnetic phenomena through 4 compact relationships. But the equations contained a surprise. When Maxwell analyzed what they implied for electromagnetic disturbances, he found that the equations predicted the existence of waves, oscillating electromagnetic fields that could propagate through space, that would travel at a specific speed determined by the electrical and magnetic properties of empty space. Maxwell calculated that speed. The electrical properties of space and the magnetic properties of space had been measured independently through completely different experiments. When Maxwell combined them according to his equations, the result was a number, approximately 310,000 kilometers per second. The speed of light, measured independently through astronomical observations and laboratory experiments, was approximately 315,000 kilometers per second. The agreement was too close to be coincidence. The realization struck like revelation. Light itself was electromagnetic wave. The same equations that described compass needles and electric sparks also describe the light by which we see the stars. The phenomena that seemed utterly different, the attraction of magnets, the discharge of lightning, the illumination of candles, were manifestations of single underlying reality. Electricity and magnetism and light were not 3 mysteries, but one. Maxwell announced this discovery with characteristic modesty. In his 1865 paper, A Dynamical Theory of the Electromagnetic Field, he wrote, "We can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena." The phrasing was careful, almost hesitant, but the implications were revolutionary. The unification was achieved. The hidden connection was revealed. The equations themselves, in modern notation, fit on a single page. 4 relationships describing how electric and magnetic fields are created by charges and currents, how they change in response to each other, how they propagate through space. the compact form conceals the profundity, the way these few symbols encode the behavior of everything from radio waves to gamma rays, from the light of distant galaxies to the signals in the neurons of your brain. The equations are among the most powerful in all of physics, describing phenomena across 30 orders of magnitude and frequency, from the longest radio waves to the highest energy radiation we have detected. But Maxwell did not live to see his equations confirmed experimentally. The electromagnetic waves he predicted, waves other than light, waves that could be generated and detected with laboratory equipment, were not demonstrated until 1887, 8 years after Maxwell's death. Heinrich Hertz, working in Germany, produced radio waves through electrical oscillations, detected them at distance, measured their speed, and found it matched the speed of light exactly. The confirmation was complete. Maxwell was vindicated. The invisible waves were real. We close this chapter contemplating what Maxwell achieved in his quiet study, working with paper and mathematics rather than with elaborate apparatus. He showed that phenomena thought separate were manifestations of single underlying unity. He predicted new phenomena, electromagnetic waves beyond visible light, that were later confirmed. He provided theoretical foundation for technologies, radio, television, radar, wireless communication, that would transform human society. And he did this through mathematical reasoning, through the belief that nature's patterns could be captured in symbols, through trust that equations describing known phenomena would correctly predict unknown ones. The equations written in starlight. The unification glimpsed through mathematics. The light revealed as electromagnetic wave. The prediction of invisible spectra waiting to be discovered. The foundation of modern physics, laid in Victorian study by Scottish physicist whose name deserves to be known as widely as Newton's or Einstein's. The equations, the unity, the revelation, forever describing the light by which we see, forever governing the forces that hold matter together, forever the foundation upon which understanding of electromagnetism rests. Maxwell's equations revealed not only what light was, but what else must exist. An entire spectrum of electromagnetic waves stretching from wavelengths far longer than visible light to wavelengths far shorter. Most of this vast range invisible to human eyes, imperceptible to human senses, yet as real as the rainbow and far more extensive. This chapter contemplates the implications of Maxwell's discovery, the recognition that visible light is merely a narrow window in a vast electromagnetic spectrum. The visible spectrum spans wavelengths from about 380 nanometers, violet, to about 700 nanometers, red. A range that seems complete because our eyes evolved to detect precisely this range, because the sun emits most strongly in these wavelengths, because this is all we can directly perceive. But Maxwell's equations contained no restriction to these wavelengths. The equations described electromagnetic waves of any frequency, from 0 to infinity, all traveling at light speed, all governed by the same mathematical relationships. The visible spectrum was special only because our biology happened to detect it, not because physics singled it out. The implications were stunning. The space around us, the air we breathe, the vacuum between planets and stars, all must be filled with electromagnetic radiation we cannot see. Waves longer than red light, infrared, than radio waves, must exist but be invisible. Waves shorter than violet light, ultraviolet, then X-rays, then gamma rays, must exist but be equally invisible. The universe was bathed in radiation we could not perceive, energy we could not detect, without instruments to translate it into forms our senses could register. Maxwell himself could not verify these predictions, could not generate radio waves and detect them at distance, could only trust the mathematics, trust that equations describing known phenomena would correctly predict unknown ones. The trust was justified, but was not confirmed until after Maxwell's death, when Hertz demonstrated radio wave generation and detection in 1887. Hertz's experiments were elegant, were definitive. He used oscillating electrical circuits to generate electromagnetic disturbances, used separate circuits to detect those disturbances at distance, measured the wave's speed and found it matched light speed exactly, measured the wave's wavelength and found it matched theoretical prediction. The invisible waves were real. Maxwell's theory was confirmed. The spectrum beyond visible light was not merely mathematical abstraction, but physical reality. The confirmation opened floodgates of discovery. Within decades, the entire electromagnetic spectrum was mapped. Infrared radiation, discovered by William Herschel in 1800 through its heating effect, was understood as electromagnetic waves longer than visible light. Ultraviolet radiation, discovered by Johann Ritter in 1801 through its chemical effects, was understood as electromagnetic waves shorter than visible light. X-rays, discovered by Wilhelm Röntgen in 1895, were recognized as still shorter electromagnetic waves. Gamma rays, discovered through radioactivity studies, completed the high-energy end of the spectrum. Each region of the spectrum brought new capabilities, new understanding, new technologies. Radio waves enabled communication without wires, enabled broadcasting that could reach millions simultaneously, enabled radar that could detect objects through darkness and clouds. Microwaves enabled cooking, enabled satellite communication, enabled the detection of cosmic microwave background radiation, the oldest light in the universe, electromagnetic echo of the Big Bang itself. Infrared enabled thermal imaging, enabled remote sensing, enabled the study of cool objects in space. Ultraviolet enabled sterilization, enabled the study of hot stars. enabled understanding of atmospheric processes. X-rays enabled medical imaging that could see inside living bodies without surgery, enabled materials analysis, enabled the determination of crystal structures. Gamma rays enabled cancer treatment, enabled the study of the most violent processes in the universe. The applications were practical, were transformative, were the basis for technologies that shape modern life. But beyond applications lay something more profound, the recognition that human perception is not the measure of reality, that the universe contains far more than we can directly perceive, that what we call visible light is merely the slice of electromagnetic spectrum our biology happens to detect. The philosophical implications deserve contemplation. If so much of electromagnetic reality lies beyond our perception, what else might exist that we cannot detect? What other aspects of the universe might be real but invisible, present but imperceptible? The electromagnetic spectrum became metaphor for hidden dimensions of existence, for the gap between what is and what we can perceive, for the humility appropriate to beings whose senses evolved for survival rather than for complete understanding. Maxwell himself reflected on these implications. In his writings, he noted the vastness of what might lie beyond human perception, the likelihood that reality exceeded human capacity to comprehend. The recognition did not lead him to despair, but to wonder, to appreciation for the mathematical tools that could reveal what senses could not detect, for the way human reason could extend human perception beyond biological limits. We close this chapter contemplating what it means to live immersed in invisible radiation. The radio waves passing through your body at this moment, carrying signals you cannot feel, but that your devices can receive. The infrared radiation your warm body emits continuously, invisible to your eyes, but detectable by thermal cameras. The cosmic microwave background filling all of space, remnant of the early universe, ancient light still traveling after nearly 14 billion years. The X-rays from distant black holes, the gamma rays from supernovae, the vast electromagnetic symphony playing constantly in frequencies we cannot hear without instruments to translate. Maxwell's equations revealed this hidden realm, showed that light was merely portion of something vaster, opened human understanding to phenomena beyond human perception. The invisible spectrum that surrounds us, that fills the universe, that carries information from the most distant reaches of space to the most intimate workings of our cells. The unity that Maxwell discovered extended beyond visible light to embrace all electromagnetic radiation, to reveal the universe as bathed in waves our ancestors could never have imagined. The invisible spectrum, the frequencies beyond our senses, the radiation that fills all space, forever present though hidden, forever carrying energy and information through the void, forever testimony to how much exists beyond what we can directly perceive. The concept of the field, that idea Faraday intuited and Maxwell made mathematically precise, represents one of the deepest shifts in human understanding of physical reality. This chapter meditates on what it means that space is not empty, that what appears to be void is actually structured, that invisible fields fill all of space and mediate all electromagnetic interactions. Before fields, physicists imagined forces acting at a distance. Newton's gravity reached across empty space instantaneously, pulling moon toward Earth and Earth toward sun without any medium to carry the attraction, without any time delay, without any structure in the intervening void. The mathematical description worked beautifully, predicted planetary motions with remarkable accuracy, seemed to require no mechanism, no explanation of how the force actually got from one object to another. Newton himself was troubled by this action at a distance, called it absurd that anyone could think gravity operated without intervening medium, but could not specify what that medium might be. Faraday's field concept changed everything. The space around a magnet was not empty, but was filled with something, with magnetic field that had structure, that could be visualized through iron filings, that actually carried the magnetic influence from place to place. The space around an electric charge was similarly filled with electric field, with structure that determined how other charges would be pushed or pulled. The fields were not mere mathematical conveniences, but were physically real, were actual features of space itself. Maxwell's mathematics made this physical reality precise. The equations described how fields were created, how they changed, how they propagated through space at light speed. The equations showed that changes in fields did not propagate instantaneously, but traveled at finite speed. That when you move a charge here, the effect on a distant charge there does not arrive instantly, but takes time. Time for the electromagnetic disturbance to cross the intervening space. Action at a distance was replaced by local action, by fields influencing nearby fields which influenced other nearby fields in continuous chain of causation. The implications were revolutionary. Empty space was revealed as not truly empty, but as arena where fields could exist, could carry energy, could transmit forces, could support waves. The vacuum itself had physical properties, electrical permittivity and magnetic permeability, that determined how electromagnetic fields behaved within it. What had seemed like mere nothing was actually something, was structured medium capable of supporting the electromagnetic phenomena that permeate the universe. The field concept would extend far beyond electromagnetism. Einstein's general relativity described gravity not as force acting at distance, but as curvature of space-time field, as geometry of space itself being distorted by mass and energy. Quantum field theory described fundamental particles as excitations of underlying fields, electrons as ripples in electron field, photons as ripples in electromagnetic field, the very substance of matter arising from field-like structures pervading all of space. But we remain with Maxwell's original insight, with the electromagnetic field that was the first to be understood, that remains the most thoroughly characterized, that governs so much of physical reality. The field between your hand and the surface it touches, electromagnetic field that prevents atoms from passing through each other, that makes matter solid, that keeps your body coherent rather than dissolving into constituent particles. The field between the sun and the earth, electromagnetic field carrying sunlight across 93 million miles of apparent emptiness, delivering energy that warms the planet and drives photosynthesis and ultimately sustains all life. The field between the transmitter and your radio, electromagnetic field carrying signal through walls and through air and through the space where nothing visible exists. What does it mean to exist immersed in fields? The question is both physical and philosophical. Physically, it means that you are never isolated, that fields connect you to everything charged or magnetic, that the electromagnetic field permeates your body and your surroundings, that what seems like separation is actually connection through invisible medium. Philosophically, it means that the universe is not collection of discrete objects interacting across empty distances, but is continuous web of fields in which objects are merely local concentrations, merely patterns in underlying medium. The poetry of fields speaks to something deep in human experience, the sense that everything is connected, that separation is illusion, that what happens here affects what happens there, through chains of influence we may not perceive. The physics confirms this intuition in specific domain, confirms that electromagnetic influences propagate through space, that fields carry energy and momentum, that the void is not void, but is filled with structure that binds the universe together. Maxwell understood the profundity of what he had discovered. In his writings, he reflected on the nature of fields, on what it meant that space had properties, on the philosophical implications of the electromagnetic worldview. He did not claim to understand what fields ultimately were, what substance, if any, they were made of, what their deepest nature might be. But he knew they were real, knew they were not mere mathematical fictions, knew that the electromagnetic field was as physical as the matter it permeated. We close this chapter contemplating the field that surrounds you now, the electromagnetic field filling the space where you sit, carrying light to your eyes, carrying radio waves past your body, sustaining the chemical bonds that hold your molecules together, mediating every interaction between the charged particles that constitute your being. The field you cannot see, but that is as real as the ground beneath you. The field that connects you to distant stars, through the light that travels from them to your eyes. The field that Maxwell revealed, that Faraday glimpsed, that fills all of space and makes the universe a continuous whole rather than collection of isolated fragments. The field, the fullness of apparent emptiness, the structure of the void, forever present, forever connecting, forever the medium through which light travels and forces act and the universe coheres. Maxwell's life was brief. He died at 48, returning in his final years to Glenlair, the Scottish estate of his childhood, where the hills and lochs had first taught him to wonder, where his journey into nature's secrets had begun. This chapter follows Maxwell through his later life, his accomplishments and his sufferings, the twilight that gathered too quickly around a mind that had illuminated so much. After his time at King's College London, where he had completed his electromagnetic theory, Maxwell accepted the position of first Cavendish Professor at Cambridge in 1871. The Cavendish Laboratory was being established as Centre for Experimental Physics, funded by the Duke of Devonshire, intended to give Cambridge the experimental capabilities that continental universities already possessed. Maxwell designed the laboratory, supervised its construction, shaped its character as institution, where theory and experiment would mutually inform each other. But Maxwell's health was already failing. He had suffered from chronic illness throughout his life, possibly related to the stomach cancer that would eventually kill him, possibly related to the intense mental concentration that characterized his work. The years at Cambridge saw continued research, continued teaching, continued correspondence with scientists across Europe. But the energy was diminishing, the illness was advancing, the twilight was gathering. In 1879, Maxwell's condition worsened dramatically. The cancer had spread, had become incapacitating, had made clear that death was approaching. Maxwell returned to Glenlair, to the landscape of his childhood, to the estate his father had built, and where his mother had died when he was 8. He was accompanied by his wife Catherine, who had been his companion since their marriage in 1858, who had assisted his research in various ways, who remained devoted through the final decline. The return to Glenlair was return to origin, was closing of circle. The hills that had sparked the child's questions now received the dying man's contemplation. The lochs that had reflected clouds now reflected Maxwell's sense that his work, though unfinished, was complete enough. The silence that had shaped his capacity for deep thought now surrounded his final meditations on what he had discovered, what remained to be discovered, what would continue after he was gone. Maxwell faced death with the Christian faith that had sustained him throughout his life. Unlike some scientists who saw religion and science as opposed, Maxwell found them complementary, different approaches to truth, different ways of understanding the universe, both legitimate and both valuable. His faith was not public or ostentatious, but was genuine, was integrated into his understanding of himself and his work, was source of comfort as death approached. His final days were spent at Glenlair, surrounded by the landscape he loved, attended by Catherine and by physicians who could do little but ease his suffering. He died on November 5th, 1879, the same age his mother had been when she died. 48 years old, his work recognized but not yet fully appreciated, his equations confirmed experimentally only after his death. The burial took place in the parish churchyard at Parton, near Glenlair, where Maxwell's parents were also buried. The grave is modest, is marked by simple stone, is visited by few who recognize the significance of who lies there. The Scottish hills received back the body of one who had perceived the universe's hidden harmonies, who had translated Faraday's visions into mathematical form, who had revealed that light was electromagnetic wave and that the spectrum extended far beyond human perception. What Maxwell knew at his death and what he did not know frame the incompleteness of any life. He knew his equations were correct, knew they described electromagnetic phenomena with unprecedented precision and completeness. But he did not live to see Hertz confirm the existence of radio waves, did not see the technological revolution his work would enable, did not see the wireless communication and electric power and electronic devices that would transform human civilization. He planted seeds whose harvest he never witnessed. The incompleteness was not failure, but was simply the condition of human existence, that we contribute to ongoing projects we cannot complete, that we participate in stories that extend beyond our lifetimes, that our work continues through others who build on what we began. Maxwell's equations would be developed further by Hendrik Lorentz, would inspire Albert Einstein's special relativity, would be incorporated into quantum electrodynamics, would continue evolving long after Maxwell's death. The work was not finished because scientific work is never finished, but the foundation was laid, was solid, was permanent contribution to human understanding. We close this chapter as twilight settles over Glenlair, as it settled in Maxwell's final days. The hills quiet in evening light, the lochs reflecting sky, the silence that had shaped a great mind, now receiving that mind back into the land from which it came. The equations left behind like messages for future generations. The work continuing without its author. The contribution made, the legacy established, the life complete, though the questions remained open. Maxwell, the Scottish hills, the Christian faith, the loving wife, the illness that ended too soon a life that had accomplished so much, the burial in the parish churchyard, the modest grave, the equations that survived their author and continue describing reality today, the Glenlair twilight, the return to origin, the closing of the circle, forever marking the end of one life, forever marking the continuation of work that transcends individual lives. Maxwell did not live to see what his equations would become, the foundation of a technological revolution that transformed human civilization, that enabled communications and devices and capabilities our ancestors could not have imagined. This chapter traces the journey from abstract mathematics to concrete technology, from equations written in Victorian study to the world those equations built. The confirmation of Maxwell's predictions came in 1887, when Heinrich Hertz, working in Germany, generated and detected radio waves. The experiments were initially motivated by pure science, by desire to test Maxwell's theory, to determine whether electromagnetic waves other than light actually existed. But the practical implications were immediately recognized. If electromagnetic waves could be generated and detected, they could be used for communication. Messages could travel without wires, could cross distances instantaneously, could reach places that wired telegraphy could not. Guglielmo Marconi transformed possibility into practical system. In 1895, he began experiments with radio transmission, achieved greater and greater distances, transmitted signals across the Atlantic Ocean in 1901. The wireless telegraph was born, then wireless telephony, then radio broadcasting. By the 1920s, millions of people were listening to programs transmitted through empty air, receiving news and entertainment and music through electromagnetic waves that Maxwell's equations described. Television followed radio. If electromagnetic waves could carry sound, they could carry images. If radio frequencies could transmit voice, higher frequencies could transmit the rapid variations needed for moving pictures. The technology developed through the 1920s and 1930s became commercially available in the 1940s and 1950s, transformed entertainment and politics and culture. The glowing screens that proliferated through the 20th century were testimony to Maxwell's equations, were devices that converted information into electromagnetic waves, transmitted those waves through space, converted them back into images and sounds at receivers. Radar emerged from similar principles. Electromagnetic waves could be bounced off objects, the reflections detected and analyzed, the location and motion of distant objects determined. The technology proved crucial in World War II, enabled detection of approaching aircraft, enabled navigation through darkness and fog, saved countless lives, and changed the nature of warfare. The equations Maxwell had derived for abstract scientific reasons became instruments of survival. The applications multiplied endlessly. Microwave ovens heated food through electromagnetic radiation. Cellular phones communicated through radio waves that blanketed the planet in invisible networks. Wi-Fi enabled wireless internet connections. GPS satellites transmitted electromagnetic signals that enabled precise position determination anywhere on Earth. Medical imaging used various electromagnetic frequencies to see inside living bodies. X-rays for bones and dense tissues, MRI using magnetic fields for soft tissue detail. Remote sensing satellites observed Earth through multiple electromagnetic wavelengths, monitoring weather and agriculture and environmental changes. each application traced back to Maxwell's equations, to the mathematical relationships he had discovered in his quiet study. The equations did not merely describe the world, they enabled transformation of the world, enabled creation of technologies that would have seemed magical to Maxwell's contemporaries. The mathematics was not just true, but was useful, was powerful, was foundation for capabilities that extended human reach far beyond biological limits. But the applications had dark dimensions as well. The same electromagnetic theory that enabled communication enabled surveillance. The same principles that allowed broadcasting allowed propaganda. The radio that brought news and entertainment also brought Hitler's voice into millions of homes. The technologies created weapons as well as tools, enabled destruction as well as creation. The equations were neutral, described nature without moral preference, but their applications served human purposes both noble and terrible. The digital revolution of the late 20th century was further extension of Maxwell's legacy. Computers processed information through electronic circuits governed by electromagnetic principles. The Internet transmitted data through electromagnetic signals in fiber optic cables and through wireless radio waves. The smartphones that billions carry are electromagnetic devices from screen to antenna, from processor to power supply. The world built on Maxwell's equations expanded to include virtually every aspect of modern technological society. What would Maxwell think if he could see this world? The question is unanswerable but worth contemplating. He would recognize the physics, would understand that radio and television and Wi-Fi and cellular networks all operated according to principles he had discovered. But the scale would astonish him. The ubiquity of electromagnetic technology, the complete transformation of human communication, the ways his abstract equations had been translated into devices that shaped daily life for billions, all would exceed anything he might have imagined in his Victorian study. We close this chapter contemplating the distance traveled from Maxwell's equations to the world they built, from mathematical symbols on paper to global communication networks, from theoretical prediction to technological transformation, from the insight of one mind to the infrastructure of civilization. The equations that Maxwell wrote govern the technologies that define modern life, the constant connectivity, the instant communication, the access to information that previous generations could not have conceived, the world his equations built, the technologies his mathematics enabled, the transformation his insight made possible, forever connecting his Victorian contemplation to our digital present, forever demonstrating that abstract truth can become concrete power, forever reminding us that mathematical physics, pursued for its own sake, can change the world in ways its discoverers never anticipated. Maxwell's achievement, unifying electricity, magnetism, and light into single coherent theory, became template for physics itself. inspiration for further unifications that continue to shape scientific understanding. This chapter traces how Maxwell's success inspired subsequent physicists to seek similar unifications, to believe that beneath the diversity of phenomena might lie deeper unity. The most direct inheritor of Maxwell's legacy was Albert Einstein, who as a young man contemplated what it would be like to ride alongside a light beam. The question arose from Maxwell's equations, from the recognition that light was electromagnetic wave traveling at specific speed. What would happen if you traveled at light speed, matching the wave's velocity? Would the wave appear stationary? Maxwell's equations seem to say no, seem to require that light always travels at the same speed regardless of the observer's motion. But this contradicted ordinary intuition about how velocities combine. Einstein resolved the paradox through special relativity in 1905, showing that space and time must behave differently than Newton had assumed, that observers in relative motion must experience time and length differently, that the constancy of light's speed required revolutionary revision of fundamental physics. The theory emerged directly from taking Maxwell's equations seriously, from trusting the mathematics even when it contradicted common sense, from the same method Maxwell himself had employed in discovering electromagnetic unification. Einstein's general relativity, completed in 1915, extended the unification further. Gravity was revealed not as force acting at distance, but as curvature of space-time, as geometry of space itself being distorted by mass and energy. The field concept that Faraday had intuited and Maxwell had made precise was extended to gravity, making space-time itself a field whose curvature determined gravitational effects. Einstein spent his final decades seeking to unify electromagnetism with gravity, to find single set of equations describing both. He did not succeed, but the attempt illustrated how Maxwell's example inspired continued seeking. The 20th century saw further unifications. The electroweak theory, developed in the 1960s and 1970s, unified electromagnetism with the weak nuclear force, one of the four fundamental forces of nature. The theory showed that electromagnetism and weak force were aspects of single underlying interaction, separate at low energies, but unified at high energies. The success earned Nobel Prizes for Sheldon Glashow, Abdus Salam, and Steven Weinberg, and demonstrated that Maxwell's unification could be extended to other forces. The Standard Model of particle physics attempted broader unification, incorporating electromagnetism, weak force, and strong nuclear force into single mathematical framework. The theory was remarkably successful, predicting particles that were subsequently discovered, explaining a vast range of phenomena with limited set of fundamental principles. But gravity remained outside the Standard Model, resistant to incorporation, a challenge that continues to occupy theoretical physicists. String theory and other approaches sought still broader unification, attempting to incorporate all forces, including gravity, into single coherent picture. The approaches were speculative, were not yet confirmed by experiment, were motivated more by aesthetic conviction that nature should be unified than by direct empirical evidence. But the motivation traced back to Maxwell, to the demonstration that unification was possible, that phenomena appearing separate could be aspects of single underlying reality, that seeking deeper unity was not fantasy, but could yield genuine scientific insight. The pattern Maxwell established, that mathematical physics could reveal hidden connections, that equations describing known phenomena could predict unknown ones, that nature's diversity might conceal underlying simplicity, became methodological commitment for subsequent physics. The belief in unification was not blind faith, but was supported by Maxwell's success and by the successes that followed. Each unification achieved made subsequent unifications seem more plausible, made the search for them seem more worthwhile. Yet the search remained incomplete. Gravity and quantum mechanics remained unreconciled. Dark matter and dark energy remained unexplained. The fundamental constants of nature remained without theoretical derivation. The dream of complete unification, of single set of equations describing all physical reality, remained dream rather than achievement. The work Maxwell exemplified continued, would continue for generations or centuries more, might never reach final completion. We close this chapter contemplating the ongoing quest that Maxwell's success inspired. The unification he achieved was beginning rather than ending, was proof of concept rather than final accomplishment. The physics that followed built on his foundation, sought deeper unities, achieved partial successes, continued seeking what remained elusive. The echo of Maxwell's unification still sounds through physics, still inspires the search for theories that would reveal the universe's ultimate simplicity beneath its apparent complexity. The unification that echoed, the relativity it inspired, the standard model it enabled, the continuing search it motivated, forever demonstrating that physics can reveal hidden connections, forever inspiring hope that deeper unity awaits discovery. Before Maxwell unified electromagnetism, he made another contribution that deserves contemplation. His work on color, his demonstration that all the colors we perceive arise from combinations of three primary sensations, his creation of the first color photograph. This chapter returns to Maxwell's earlier work, exploring his investigation of how we experience the world. Color seems immediate, seems given, seems to be property of objects themselves. The red of the apple, the blue of the sky, the green of the grass, these seem to exist in the world, to be features of external reality that we passively perceive. But Maxwell's work on color revealed something more subtle, that color exists not in objects but in minds, that light has frequencies but not colors, that the experience of color is constructed by our visual system from physical stimuli that contain no color in themselves. The investigation began in the 1850s, when Maxwell applied the same systematic mathematical approach to color that he would later apply to electromagnetism. Building on earlier work by Thomas Young and Hermann von Helmholtz, Maxwell investigated how colors combine, how mixtures of light create perceptions different from the components, how the eye responds to different wavelengths. He constructed color-matching experiments, devices that allowed precise measurement of how much of each primary color was needed to match any given test color. The results were striking. Maxwell demonstrated that all colors we perceive can be created by mixing appropriate amounts of 3 primary lights: red, green, and blue. This trichromacy implied that the human eye contains 3 types of color receptors, each sensitive to different range of wavelengths, whose combined responses create our color experience. The rainbow, that seemingly continuous gradation of hue, was actually being constructed by 3 distinct biological sensors whose outputs were being combined in the brain. Color blindness, Maxwell showed, resulted from deficiency in one of these 3 receptor types. People who could not distinguish red from green lacked the receptor that distinguished between those wavelengths. The condition was not failure of attention or training, but was physiological, was structural, was consequence of missing biological equipment. The demonstration connected color perception to specific biological mechanisms, grounded subjective experience in objective physiology. Maxwell also created the first color photograph, demonstrating in 1861 that photography could capture color rather than merely shades of gray. The technique was cumbersome, required taking 3 separate photographs through red, green, and blue filters, then projecting them superimposed through the same filters. But the principle was established. Color photography was possible because color perception depended on 3 components, because matching those 3 components reproduced the color experience, because what seemed continuous could be captured through discrete sampling. The philosophical implications deserve contemplation. If color is not in the world but is in the mind, what else might be similar? What other qualities that seem to be features of external reality might actually be constructions of our nervous systems? The taste of sweetness, the smell of roses, the sound of music, are these in the world or in us? Maxwell's work on color did not answer these broader questions but opened them, suggested that the relationship between experience and reality was more complex than naive perception suggested. The work also demonstrated Maxwell's characteristic approach, the same combination of mathematical precision and physical insight that would produce electromagnetic unification. He did not merely describe color phenomena, but explained them, revealed underlying structure, showed how apparent complexity arose from simple principles. The method was the same, whether applied to color or to electromagnetism. Seek mathematical description that captures observations. Follow the mathematics to see what it implies. Trust the equations, even when they reveal surprising truths about familiar phenomena. We close this chapter contemplating the light entering your eyes at this moment. The electromagnetic waves of specific frequencies that Maxwell's equations describe, that travel from sources to your retinas, that stimulate 3 types of receptors, whose responses are combined by your brain into the seamless color experience you perceive. The rainbow is not in the sky, but is in your mind, constructed from physical stimuli according to principles Maxwell understood. The color of starlight, the reddish hue of cool stars, the bluish hue of hot stars, arises not from colored substances in the stars, but from frequencies of electromagnetic radiation that your visual system translates into color experience. Maxwell understood both the physics and the perception, understood that light was electromagnetic wave, and also understood how that wave became color experience. The dual understanding was characteristic, was integration of physical and perceptual, of objective and subjective, of mathematical description and biological mechanism. The color of starlight, the perception that constructs experience, the 3 receptors that create the rainbow, the first color photograph that proved the principle, forever reminding us that experience is not passive reception, but active construction, forever connecting Maxwell's work on color to his work on light itself. What Maxwell did not say may be as significant as what he did. The questions his equations raised but could not answer, the mysteries that remained even after unification was achieved. This chapter contemplates the silence between the equations, the not knowing that persists alongside remarkable knowing. Maxwell believed in the ether, an invisible substance filling all space through which electromagnetic waves propagated. The belief was reasonable for his time. Water waves required water, sound waves required air, and by analogy, electromagnetic waves seem to require medium through which to wave. Maxwell devoted considerable effort to constructing mechanical models of the ether, seeking to understand what properties this medium must have to support electromagnetic wave propagation at the speeds his equations demanded. But the ether was never detected. The famous Michelson-Morley experiment of 1887 sought to measure Earth's motion through the ether by detecting differences in light speed in different directions. The experiment found no such differences, was repeated with increasing precision, consistently found no evidence for the ether's existence. Einstein's special relativity, drawing on these null results and on careful analysis of Maxwell's equations, abandoned the ether entirely. Electromagnetic waves propagated through vacuum, through apparent nothingness, without requiring any medium at all. The conclusion was strange, is still strange. Waves without medium, oscillations without anything oscillating, fields filling space without substance to carry them. Maxwell's equations work, predict phenomena with extraordinary precision, but the question of what is actually waving, what the fields are made of, what fills the void through which electromagnetic radiation travels, remains without fully satisfying answer. Quantum mechanics added further mystery. Light, revealed by Maxwell as electromagnetic wave, was also revealed by 20th century physics to be composed of discrete particles, photons, that carry specific amounts of energy depending on their frequency. The wave-particle duality seemed contradictory, seemed to require that light be both continuous wave and discrete particle, both spread through space and localized in points. The mathematics handled this duality through quantum field theory, which described photons as excitations of underlying electromagnetic field. But the conceptual strangeness remained. What was light? Wave or particle or something that transcended both categories? The questions multiplied. Why did Maxwell's equations take the particular form they did? Why did nature choose these mathematical relationships rather than others? Why did electric charge exist at all? And why did it come in discrete units? Why did the fundamental constants, the speed of light, the electric permittivity of vacuum, the magnetic permeability of vacuum, have the values they had? The equations described but did not explain, captured how electromagnetic phenomena behaved, but not why they behaved that way. Maxwell himself acknowledged these limitations. His writings showed awareness that mathematical description was not the same as ultimate understanding, that successful equations did not mean physics was complete, that mysteries remained no matter how much was explained. He was humble about what his work achieved, recognizing it as contribution to ongoing inquiry rather than final word on the nature of reality. The humility was appropriate and remains appropriate. Physics has advanced enormously since Maxwell's time, has discovered quantum mechanics and relativity, has developed standard model, and explored possibilities beyond it, has achieved unifications Maxwell could not have imagined. But the fundamental questions persist. Why does the universe have the mathematical structure it has? Why do the equations that describe reality take their particular forms? Why is there something rather than nothing? And why does that something obey mathematical laws? The silence between the equations is not failure, but is simply the condition of human knowledge. That each answer generates new questions, that explanation at one level requires explanation at deeper level, that understanding is always partial, always incomplete, always surrounded by mystery that resists penetration. Maxwell's equations describe electromagnetic phenomena with stunning accuracy, but they do not explain why those phenomena exist, why they behave as they do, why the universe contains electromagnetic fields at all. We close this chapter contemplating the mystery that persists. The equations work, the predictions succeed, the technologies function, but the ultimate nature of electromagnetic reality, what fields are made of, why they exist, what they mean, remains wrapped in silence that no equation has yet penetrated. The silence between the symbols, the not knowing that surrounds the knowing, forever reminding us that physics describes but does not ultimately explain, forever preserving mystery at the heart of understanding. Light from distant stars, traveling for millions of years through the void, arrives at Earth carrying information about its origin, information encoded in frequencies and polarizations, in the electromagnetic signatures that Maxwell's equations describe. This final chapter contemplates the cosmic implications of Maxwell's work, the way electromagnetic theory connects us to the universe's farthest reaches and earliest moments. The light arriving from the night sky has traveled immense distances. The nearest star beyond the Sun, Proxima Centauri, is about 4 light-years distant. Its light has traveled 4 years to reach your eyes. The stars visible with naked eye are hundreds or thousands of light-years distant. Their light left them when ancient civilizations flourished or before humans existed. The Andromeda Galaxy, visible as faint smudge to unaided eye, is 2.5 million light-years distant. Its light left when human ancestors were just beginning to walk upright. All this light is electromagnetic radiation, governed by Maxwell's equations, traveling through the void at the speed Maxwell calculated. The light carries information about its source, about the temperature and composition and motion of the stars that emitted it. Spectroscopy, the analysis of light's frequencies, reveals what elements are present in distant stars, reveals how fast they are moving toward or away from us, reveals the physics occurring in places we will never visit. Almost everything we know about the universe beyond Earth comes through electromagnetic radiation that Maxwell's equations describe. The cosmic microwave background is perhaps the most remarkable electromagnetic signal of all. This is radiation from the early universe, emitted about 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and light to travel freely. That radiation has been traveling through space for nearly 14 billion years, has been stretched by cosmic expansion from visible light to microwave frequencies, fills all of space as faint electromagnetic glow. The radiation carries information about the universe's infancy. about conditions when the cosmos was young, about patterns that would eventually become galaxies and clusters, about the physics of the Big Bang itself, Maxwell could not have imagined cosmic microwave background radiation, could not have conceived of Big Bang cosmology or the expanding universe, or the ages of time his equations would come to describe. But the equations he derived apply perfectly. The same mathematics that describes radio stations and electric motors also describes radiation from the universe's birth, also describes light from the most distant galaxies, also describes electromagnetic phenomena across billions of light years and billions of years. The universality is striking. The equations Maxwell derived in Victorian England, based on experiments conducted in British laboratories, describe electromagnetic phenomena throughout the observable universe and throughout cosmic history. There is no indication that electromagnetism behaved differently in distant galaxies or in the early universe. The laws appear to be the same everywhere and everywhen, to be fundamental features of reality rather than local approximations. What this means philosophically is worth contemplating. The success of mathematical physics, the ability of equations derived from local observations to describe phenomena throughout cosmos, suggests that the universe has mathematical structure, that reality obeys laws, that the same principles operate everywhere. The suggestion is not proof. We cannot visit distant galaxies to verify that electromagnetism works the same way there. But the consistency of observations across cosmic distances and cosmic times provides strong evidence for the universality of physical law. Maxwell's work participates in something eternal, something that extends beyond his brief life, beyond human civilization, beyond Earth itself. The equations describe phenomena that preceded Earth's formation and will continue after Earth is gone. The electromagnetic radiation they describe has been traveling since the universe began and will continue traveling as long as the universe exists. The contribution Maxwell made was not just to human knowledge, but to the cosmic story of which human knowledge is small part. We close this final chapter contemplating light traveling through the void, light from stars that existed before Earth, light that will continue after humans are gone, light that carries the universe's story across distances and times that exceed human comprehension. Maxwell's equations describe that light, govern its propagation, predict its behavior. The equations connect us to the cosmos, make us participants in universal patterns, reveal that the mathematics we discover reflects structures built into reality itself, the light that travels still, the equations that describe it, the connection to distant stars and ancient times, forever carrying information across the void, forever obeying the mathematics Maxwell discovered, forever testimony to the unity of physical law and the reach of human understanding. James Clerk. Maxwell died in 1879, was buried in a Scottish churchyard, left behind equations that changed the world. The equations survive him, govern technologies he could not have imagined, describe phenomena across cosmic distances and cosmic times. The light that traveled while he lived continues traveling now. The unity he discovered continues revealing itself through physics that builds on his foundation. The symphony plays on. The invisible music sounds through every corner of space. The equations describe it still. And somewhere in the mathematics of electromagnetic fields, in the unity Maxwell discovered, something sacred whispers. The order underlying apparent chaos, the pattern beneath surface diversity, the light that binds the universe together, and that Maxwell, through genius and devotion, learned to hear. Conclusion: where light becomes silence. The journey ends where all journeys end, in silence deeper than words, in contemplation of what has been revealed and what remains hidden, in the recognition that understanding is gift but never completion. We have followed James Clerk Maxwell from Scottish childhood to Cambridge training, from Faraday's visions to mathematical unification, from equations written in quiet study to technologies that transformed civilization, from the electromagnetic spectrum to the cosmic microwave background. What have we learned? That one human mind, properly trained and persistently curious, could perceive unity beneath diversity, could translate physical intuition into mathematical precision, could reveal that light and electricity and magnetism were aspects of single underlying reality, that mathematics is not mere calculation, but is language capable of expressing truths that ordinary words cannot capture, is window onto structures built into reality itself. That scientific discovery connects to cosmic reality, that equations derived from local observations describe phenomena throughout the universe and throughout time. We have learned that genius does not guarantee long life or complete understanding. Maxwell died at 48, did not see his predictions confirmed, did not see the technologies his work enabled, did not see the further unifications his success inspired. The incompleteness was not failure, but was simply the condition of human existence, that we contribute to projects we cannot complete, that we participate in stories extending beyond our lifetimes. We have learned that mystery persists even after remarkable discovery. Maxwell's equations describe but do not explain, capture how electromagnetic phenomena behave but not why they exist, reveal mathematical structure but not ultimate meaning. The silence between the equations, the not knowing that surrounds the knowing, remains, will always remain, testimony to the limits of human understanding and to the depth of reality that exceeds our grasp. As sleep approaches, as consciousness dims toward dreams, we carry these lessons with us. Carry the image of the Scottish boy asking questions that would change the world. Carry the vision of fields filling space, connecting everything to everything. Carry the recognition that the light traveling from distant stars obeys the same equations that describe the spark between your fingers on a winter's day. The light that binds the universe, electromagnetic field permeating all of space, carrying energy and information across cosmic distances, governed by equations that one human mind discovered through the same curiosity that first stirred in the hills of Glenlair. The unity that Maxwell revealed continues revealing itself. The symphony plays on in frequencies beyond our perception, in wavelengths that carry the universe's story, in the endless propagation of electromagnetic waves through the void. Sleep now. Dream of light traveling through darkness, of equations that capture truth, of one mind perceiving what had been hidden since the universe began, of the connection between what seems separate, the unity beneath diversity, the invisible symphony that sounds through all of space and time. Maxwell's equations endure. The light travels still. The mystery deepens even as understanding grows. And somewhere in the silence between the symbols, in the space where mathematics meets meaning, the universe whispers its secrets to those who learn to listen. The invisible symphony, the unified field, the light that was and is and will be, forever traveling, forever obeying, forever binding the universe together in harmonies we are only beginning to hear. Good night. Sleep deeply, and wake remembering that you exist within electromagnetic fields, that light carries the universe's story to your eyes, that the same equations governing distant galaxies govern the neurons firing in your brain. You are part of the symphony. The light connects you to everything. Rest now. The equations will still be true when you wake. The light will still be traveling. And the mystery Maxwell glimpsed, the unity beneath the diversity of phenomena, will still be waiting, still inviting contemplation, still revealing itself to those who look with patient eyes and curious minds. The dawn will come, the light will continue, and the invisible symphony plays on.